So now let's try to understand the origin of nonlinearity, from where we can start telling our computer model that now the action and deformation relationship is no more linear. At what level, right? So I urge you to always think of the structural hierarchy in terms of this. First you have materials. Just consider any finite element program and the process of how you construct a computer model. It follows exactly that hierarchy, that you start with defining material properties. Those material properties are called in while defining the cross-sectional properties. So when you are defining a cross-section, you tell the program that this cross-section should be associated with that material, right? And then next, first level is material level, then cross-section level, third level is member level. In member level, when you define a member, the cross-section property is called in that member definition. For example, when you start defining a beam or a column, you have to tell which cross-section is associated with that member, right? And that cross-section is already having a material associated with that, right? So you define material, you call that material and define cross-section, you call that cross-section and define member or draw member, right? Complete the geometry, and now you have the full structure. So material, basic level, material, next level cross-section, and then next level member, and final level is structure, right? Just consider a simple K matrix and you will understand that hierarchy. I take this two-dimensional frame element with 3 degrees of freedom at both ends as an example. Total 6 degrees of freedom. This is a two-dimensional, so out of plane degrees of freedom are ignored. Otherwise, a 3-dimensional frame element have 6 degrees of freedom at each end. So its real K matrix is 12 by 12. But let's take this two-dimensional as an example, and we have 6 by 6 K matrix. Just check what input is required to construct this K matrix. EAIL. It is frame element, so no need of Poisson's ratio or some other. If you go for a shell element, area element, you will see some other inputs also, but those can also be accommodated in these 3 categories. So E is what? A material property, which means that when the program is constructing K matrix, from material it only requires E, right? And I am talking about linear modeling. K matrix means a constant K matrix, which means the model is linear. So if the model is linear, from material side, software only requires one number, E, for your material. From the cross-section level, next level, first is material, then cross-section, you require only 2 properties, A and I. Both are the functions of cross-sectional dimensions. So once you give the cross-sectional dimension, program calculate that and it requires that in K matrix. And member level, you require length. Length is an example of a member property. AI are an example of a cross-sectional property. E is an example of a material property, right? So when you draw a particular member, software know that what is its length, right? So all the information to construct K matrix is available with the program. This is linear elastic modeling, right? If we want to make this beam as non-linear now, we can include the effect of inelastic action at any of these 3 levels: material level, cross-section level, member level, because the stiffness is derived from these 3 levels. Material stiffness is being used, E is being used in the cross-section definition. So material stiffness is contributing to cross-section stiffness. Cross-section stiffness is contributing to member stiffness, and member stiffness is contributing to full global K matrix of the structure, full structural stiffness. So simply by understanding the flow of stiffness from material to full structure level, you can also guess that at what level I have the opportunity to introduce the nonlinear action in this flow, so that the relationship between F and U may not remain linear, right, as assumed in this case, right. So once you understand and same is the case for area elements like shell element, just check its K matrix. All the things which are required to construct that K matrix, they will either be material property or cross section or member. Like Poisson's ratio is required in certain area elements, it is a material property. Shear modulus is required, it is a material property, G, right. Similarly, some other properties may be required which can be cross sectional, which can be member level. So once you understand the composition of structural stiffness, you can guess that at what effort is required to include inelastic action in that composition, right. So this is the summary of same thing, that material stiffness and cross-sectional geometry, they combine to make cross-sectional stiffness. Cross-sectional stiffness and member geometry, they combine to make member stiffness, and member and structure make structure stiffness, right. So material stiffness is what? Currently we know one number, E, but actually it is the resistance of material to strain. Section stiffness is what? Currently we know I, bending inertia, but actually it is the resistance of that cross section to overall strains or deformations. Similarly, member stiffness, sometimes we say EI is the combined cross section stiffness, flexural stiffness, and EI over L is the member stiffness. So you see here, E was the material stiffness alone, then a property from the cross section shape joins that and make what we call as cross sectional stiffness, and then a property which is the property of member, which is length, it joins that, and now we have this member stiffness, right. And then all the elements, they are joined to make structural stiffness. So the point is that the relationship between action and deformation, which means these stiffnesses, they can be variable or constant. Stiffnesses can be constant for linear case, and they can be variable for non-linear case. For just like for material case, let's take an example. A material follows Hooke's law, sigma is equal to E into epsilon, and because of that we call this E as the stiffness of that material, right. Now in a complete stress strain behavior which is non-linear, E is variable, right, E is variable. So this equation was being used in a linear model, while this complete relationship, complete nonlinear curve will be used in a nonlinear model, right. So this is an example of how a stiffness which is relating the action and deformation can be constant and can be variable. Now in a nonlinear computer model, we have to define nonlinear stiffnesses or the nonlinear relationship between action and deformation, right. But we can do that at any of these three levels. If we directly define the material as nonlinear, no need to define cross section and member as nonlinear, because whatever is the net effect of inelastic action, it will manifest at higher levels. Material is the most fundamental level. So a nonlinear stress strain curve, if it is given to your material, then no need to do anything, it will manifest the nonlinear action at higher levels. Another approach could be that let's not disturb material. Let's directly define the nonlinear section stiffness, which means the relationship between cross-sectional action and cross-sectional deformation. We can define it as a nonlinear and give it as an input, right? So material will not be nonlinear now, but the program will know that at cross-section level the nonlinear action should be accounted, and that cross-section level nonlinearity will automatically manifest at member level and at full structure level. A third approach can be that you directly define member stiffness as nonlinear. Leave the previous two levels as it is. Directly tell the program that the member bending moment and the member rotation, for example, the relationship between them is this nonlinear relationship which you give as an input. So do not disturb the first two levels. Directly define the member level action versus member level deformation nonlinear behavior as an input, right? So we can define the nonlinear action at any of these three levels. Any of these approach will result in a nonlinear structural stiffness, right? But if we do it at material level, it will be the most fundamental level. But we can also do it at second level or third level, right? I will classify the nonlinear modeling approaches based on this idea also. First, I give you a classification which was based on how we account nonlinearity, right? Using lumped approach or concentrated approach or distributed or continuum approach. But there can be this classification also. Obviously, if you are using continuum models, then you are at this level. You are directly defining material nonlinearity right at material level, and also distributed or fiber approach also. You are defining material at the most fundamental level. You are defining the nonlinear action deformation, which is actually the stress strain curve of that material, right? The concentrated plasticity approach, you can go for these two levels. You can put a hinge in your computer model and directly define the cross-section action, cross-section deformation relationship to it. No need to modify material or make it nonlinear. Or in the same concentrated plasticity approach, you can also define directly the member action versus member deformation as the nonlinear action deformation behavior. So these two levels we can have in the concentrated plasticity approach, and the first level we can account the inelasticity in the first level while using continuum approach or distributed approach or fiber approach. So this is same thing, that each of the level can be linear or can be nonlinear, right? So we can define directly the material stiffness as nonlinear, or we can define the cross-sectional stiffness as nonlinear, or we can define member stiffness as nonlinear. In any of these three approaches, the structure at the end will be nonlinear, right? So the green line, the blue color is showing you the linear part or possibility of this being a linear property, and this orange is showing nonlinear. So I can say that this part, this material nonlinear approach, is actually the continuum approach or distributed plasticity approach, because in these two approaches you directly make the material nonlinear and no need to do anything else, no need to modify the model at a higher level, right? You directly make steel nonlinear, concrete nonlinear, and let that manifest at cross-section member structure levels. But in the plastic hinge approach or concentrated hinge approach, this is the domain of that plastic hinge approach. Plastic hinge approach, that you put a plastic hinge in your computer model at certain location, and the element between two plastic hinges is linear, model is only having lumped plasticity at those plastic hinge locations, and those plastic hinges have the action deformation curve they can have at cross section level. For example, cross sectional moment versus cross sectional deformation, which is curvature, or member level moment and member level deformation, which is rotation, right? So member versus member and cross section level, they can be made non-linear using plastic hinge approach. It depends on what type of hinge we are using. Some hinges are for cross sectional level non-linearity, some are for member level non-linearity. So when we define the inelastic behavior at material level, this is fiber modeling approach, right? So if I have to define one in a fiber modeling approach in one line, I can say that it is the type of modeling in which directly the material stress strain curve is provided as an input, which is nonlinear stress strain curve, right? And when I say nonlinear curve, please keep in mind that it is not just backbone curve, it is also the cyclic behavior, how the material will behave or action will behave in one go, or also how it will behave if I give cycles of loading, unloading and reloading. So the main monotonic behavior is called backbone curve, and the reloading, unloading, that behavior is called hysteretic behavior or hysteretic rule. So the complete nonlinear behavior is defined by both of these things, not only one curve. So when I say moment rotation behavior, it is moment versus rotation curve in backbone also, and also the cyclic moment rotation, and also in both directions, right? Positive moment and negative moment, similarly positive action and negative action, positive deformation and negative deformation. So we will not discuss continuum approach from now onwards, only distributed plasticity, which means fiber modeling approach, and the concentrated plasticity, which is the plastic hinge approach, and that can be at two levels, cross section level and member level, right? So in that also we will mostly focus on member level, right? So because we will be using those types of plastic hinges which will have a direct member level action versus member level deformation as an input, right? So actually, if I summarize, I will be focusing on two nonlinear modeling approaches for RC element. Fiber approach, in which we directly make a nonlinear material. Now that material can be defined to a beam or a column or a shear wall, that will be called as a fiber model of a beam, or a fiber model of a column, or a fiber model of a shear wall. And the second approach is plastic hinge approach, in which we will directly lump the inelastic action at member level, right? At member level. So we will not discuss much about cross section level, directly at member level, right? So beams, columns, shear walls, they can be modeled either using fiber approach, or they can be modeled using member level plastic hinge approach. The difference will be same. Let's assume one column. In fiber approach, I will directly make the concrete and steel of that column as nonlinear, and that stress strain curve, nonlinear stress strain curve, will automatically take care of the effect of cracking, yielding, crushing, anything. If I model the same column using the plastic hinge approach, I will lump that at two ends of that column for a reason which I will explain in next class, and I will give a directly member level moment versus rotation behavior of that column at those 2 points, right? And that nonlinear action deformation moment versus rotation will be accounting the effect of cracking, yielding and everything implicitly, right? Because ultimately if you go to the material level, the failure is only at material level. For example, when I say flexural yielding, now flexural is a member action. Flexural yielding is the yield of whole beam, but at a most fundamental level it is material failure, that a particular bar in that beam will fail in tensile yielding, right? So in plastic hinge approach, where I will be giving two hinges at both ends for that column, the effect of cracking, yielding, crushing is implicitly accounted in the form of the plastic hinge properties, and that property is directly at member level, which is moment versus rotation theta, nonlinear behavior. Here and here also nonlinear behavior. So this yield point, when I define, it automatically accounts for the effect of cracking, yielding and everything. All the material failure is implicitly accounted in that yield point, because that yield point is a function of Fc prime, Fy is a function of amount of steel and everything, right? So in fiber approach, we directly make a material nonlinear. For example, this is now plastic hinge model. Fiber model will be like this, that now the whole material is nonlinear, right? So everywhere you have a governing stress strain relationship. If there is a bar inside which is passing through like this, the bar will have a relationship like bilinear, whatever is the steel stress strain curve. Any point of concrete will have a concrete stress strain curve, right? So whatever is the effect of cracking, yielding, it will be distributed along the length and it is automatically accounted. But the second approach, this one, plastic hinge approach, there will be an elastic element in between, and the inelasticity is lumped or assumed only at two ends, and at those two ends there is a direct lumped behavior, moment versus rotation, which implicitly account. Implicitly means not directly but by some other means, indirectly, right? So it accounts for the effect of material failure or any other action of nonlinearity. When you say that beam will yield at this point, beam will have ultimate failure at this point, when you define that curve, you automatically account all those failures, you just lump them as one curve, right? So this second approach, right one, let's say it is A, this is B. This approach B is more simple. It only requires you to construct plastic hinge moment rotation curve. Obviously there are some complexities involved in case of column, but let's say it is a beam. Only all you need to have is a moment rotation curve which is at two ends of that beam. Now that moment rotation curve will be a function of everything: beam cross section size, it will be a function of amount of steel in that cross section, it will be the function of Fc prime, Fy. So it is a directly member level stiffness, member level action. So it automatically have the cross section level properties in it and the material level properties in it. So you will see that if you want to calculate this point mathematically, you will see that you will require Fc prime, you will require Fy, which are material properties, you will require E, you will require cross sectional properties like cross sectional dimensions B, D, and a lot of other inputs are required. So the whole member behavior is just combined in the form of one curve. So this curve is the whole life, you can say is a whole lifetime of this member, which is telling you that what will be the condition of this member or this column at different moments. It tells us that at what moment it will yield, at what moment it will have its ultimate capacity, at what moment it will just collapse. Now this curve we just take, give it in the program as an input to that plastic hinge. So now program have everything it have the complete capacity of your beam or a column. So demand it will calculate from the applied loading, and capacity you provide it. Now it have everything to compare. Demand and capacity are compare, and the performance can be directly given at the end of the analysis by that program, right? So this is a quick overview. Obviously we will go into detail of these two approaches, fiber modeling approach and plastic hinge approach. They are parallel approaches. Obviously in the same computer model you can decide that shear wall I can model using fiber approach, and beams I can model using plastic hinge approach. You can do that, but it's not that you will be using the fiber and hinge approach together for the same element, right? They are parallel nonlinear modeling approaches. So at the end, let's see this one more classification. Obviously I will not go into its detail. I'll just show you. This is similar classification, but now from a different reference, NIST report. It is also available. Please check that report about nonlinear modeling. So this is same classification but in a more expanded manner. On one extreme we have a detailed finite element kind of a model, where you have very small discretized elements. Each element have a specific behavior. On the other extreme left, you have the plastic hinge approach, where you have a nonlinear, you have a linear element, and all the nonlinear action is lumped at certain hypothetical points, and those points are defined in a computer model in the form of hypothetical elements, zero length elements, which are called plastic hinges. In between them can be several other approaches also. For example, nonlinear spring hinge, it is very similar to this one. Finite, these two are actually the distributed plasticity approaches. The plasticity is, in this particular C case, the plastic action is distributed for some part of the length, and in between those two parts is a linear element. But for D, it is a complete fiber section, which means along the whole length we have nonlinear action, but not in a detailed manner like E, but in a simplified manner using material stress strain behaviors, right? So in between these two extremes A and E, there can be some mixed approaches also, but we will be using only two approaches. If I talk about this particular figure, I will be focusing on D, fiber modeling, and in that the fiber can be extended to the whole length of the element or some part of the length. And second approach, I will be focusing on this A, plastic hinge approach for beams, columns and shear walls. Similarly, fiber approach for beams, columns and shear walls, right? So please go through that discussion. I will not go into its detail, but it tells us some information about this report. Actually tells us information about how we should decide which approach to use. This report also provides a flow chart to systematically decide about the nonlinear modeling approach. I will show you at the end. So this is same discussion. Hinge or spring models are concentrated plasticity. You required predefined action deformation relationships to give as an input. Fiber type approach is in between continuum and hinge or spring model. It is based on defining the material level nonlinear behavior, but not as detailed as continuum. And finally, other extreme is continuum, where you represent the behavior at the most fundamental level, right? So you define it in a very discretized small manner. So some limitations of this continuum finite element models, they cannot be used in most practical cases. So we will have distributed plasticity or lumped plasticity approach. So this is that flow chart that you first start with element modeling, you first decide whether you require detailed modeling or not. If you require detailed modeling, which means micro modeling, go for the continuum model approach. Otherwise, you should go for discrete model, and in that you should have again two options: force control or deformation control. Some actions can be assumed force controlled, which are brittle actions. Some actions can be assumed deformation controlled, which are ductile actions. If force controlled is the element is force control, then you have to decide whether you have to model that using a linear element, or you have to actually check. If you do not model that, you have to check that non-simulated failure mode. Let me give you an example to explain this. Let's say that I have a beam, and beam can have a chance of having shear failure during the applied earthquake, right? Let's say it can fail in shear. It have that reinforcement and everything, that if the load is exceeded, it will fail in shear. Now I have two options. Either I explicitly make that shear deformation action versus shear deformation, I assume it as non-linear and define a shear hinge, right? It can be linear hinge or a non-linear hinge, right? But shear behavior is explicitly, I include it in the form of a hinge. In that case, the model will automatically tell whether the shear failure has occurred or not, because I defined hinge in it, and hinge is I am giving my own capacity to the program to compare it with the demand. So this is a simulated action. Now shear failure, now the model have the capacity to tell whether the shear failure have occurred or not. If you define it as a deformation control, you will give a complete shear deformation versus shear action curve. So it will not only tell whether shear failure have occurred or not, the program will be able to tell how far it go beyond the capacity, right? This is when you define shear as a deformation controlled action. Let's assume that I want to make my model simple and I assume it to be a force controlled action. In that case, I will still include a hinge, but in that case, that hinge will simply contain the shear capacity in the form of shear force capacity. The program in that case will simply be able to tell me whether the shear failure have occurred or not. It will not be able to give me the complete picture how far it went beyond the capacity or not, right? So this is first approach is deformation control, where you completely simulate that action non-linear. Second is that you assume it as force control and model it as force control here. In that case, the model will be simply able to detect whether the force capacity have exceeded the demand or not, or demand is more than capacity or not. In that case also, no need of a manual check. The program will be able to tell after the analysis whether that beam is yielded in shear or failed in shear or not. The third case is that I assumed shear failure to be a force control behavior and I didn't model it explicitly using a hinge, right? This is the default case. When you do not take care of shear, this is the line you are taking actually, unless you define a hinge for shear, right? In that case, you have to manually check that non-simulated failure mode. Shear is one example. I can give another example also. So in that case, what you have to do, the program will not be able to detect shear failure because no hinge there, either force controlled or deformation controlled. So this is a non-simulated action now. This action program is not able to detect. So you have to manually compare the shear force demand with your shear force capacity and check whether that shear failure have occurred or not manually. Program will not help you in this, right? So this is what we do in default. Even in linear modeling also, what we do, we run the analysis. Since there are no hinges, program don't know what is shear failure. It simply report the shear force in all the elements. Then we compare that shear force with the shear capacity of each element to check whether shear failure will occur in reality or not, right? So this is that third line, that force control action is not simulated, so you have to check it as a non-simulated failure mode. Shear is one example of that, right? So in linear elastic modeling, we will always be like this, like bending moment. When the linear elastic model reports bending moment diagram, it doesn't tell that whether the capacity is enough to handle that bending moment or not. We have to do it manually if we want to do it, right? So flexural DC ratios, we have to calculate manually if we want to, because the flexural failure is a non-simulated mode, is a non-simulated failure mode in that linear model. So then you proceed for deformation. Again you have to take a decision between fiber modeling approach or concentrated plastic hinge modeling approach, right? So this is our case. If we go for fiber approach, then a separate thing. If you go for concentrated approach, then a separate consideration, right? So two main decisions you have to take for each action versus deformation behavior, whether that should be modeled as a force controlled action or a deformation controlled action, right? Whether you want to see the complete picture after the failure also, or you just want to detect that failure, right? Brittle failure, obviously the actions which are ductile, you will go for the deformation controlled behavior. For brittle failures, you know that the yield point is the ultimate failure, there is no post peak thing, so which means you should declare it as a force controlled action. Then once you define it as a deformation controlled, again you have to decide between fiber modeling approach or plastic hinge approach. In the force controlled actions, you have to decide whether I have to define a force control hinge or no need to define that. If you define a force control hinge here, in that case the program will be able to detect that failure but will not be able to tell afterwards. If you don't model that force controlled action, you have to manually check whether that failure would have occurred or not, right? So program will not tell. So two main decisions, force controlled versus deformation controlled, and within each of them again two decisions. In force control, whether you want to use a force controlled hinge or just leave it as it is, and second in the deformation control, whether you want to go for a more fundamental fiber approach or a lumped member level plastic hinge approach, right? So this was an overview of all the approaches, right? We will go into more detail in next few sessions, and then a practical demonstration of how to include a plastic hinge in the program, in the model, how to give it a force deformation behavior as an input, right? And there how many types of hinges are there, for example, that we will discuss in next session.